This is the third part of lecture 6. In the first part, I had introduction for radio propagation modeling for wideband applications, and in the second part, I gave two specific examples. One was GSM model, and the other one was JTC model. This third part is related to the so-called wideband models for local area networks. That's what I have called it in here. And by that, I mean the wideband models which are used for local area networks, or the ones that are in the process of, or they are the foundation of what is like models developed for local area networks. The first model is 802.11b model. The second model is a 802.11n model, but 802.11n is for MIMO. But at the beginning of that standard, they have a SISO model also. SISO is single input, single output, single transmitted output, single received output, and they have a path loss model for that. That is actually a complement to 802.11b model. So these two together are really one model. Here is the path loss, here is the channel profile. And then I start to talk about the so-called Saleh-Valenzuela model, which was developed in Bell Laboratories in mid-1986 or 87. And this model, when it was done, actually, a lot of research started after that. But it was not included in the standards. And some of actually my students also started around expanding that particular model. It was there actually in terms of being applied into the standards until like past 2-3 years, which people started to look into the MIMO modeling and also modeling for ultra wideband. At that time, the work by Saleh-Valenzuela and also follow-up work that I will study a little bit later, and part of that was done with my students, are the next part that we discuss, okay, which is like foundation of what is emerging for ultra wideband and 802.11 and MIMO and ultra wideband modelings today. But the model for 802.11b and SISO model for 802.11n is very similar to the GSM and also JTC model. There's not much of a difference, but in here, since the area is only like indoor areas, they have a different approach in partitioning. So we are coming to 802.11b model. Basically what they have is they have this delay power spectrum. If you remember, for example, for GSM or for like for the JTC model, they were dividing the areas first into indoor, outdoor, and then for each of them they had a different profile. And then like indoor areas, they were dividing the indoor areas in like residential, commercial, and offices, and then for each of them they had different profiles defining. In here they define one single profile in which you can change the RMS. Since all of the application for 802.11b are considered to be indoor, so this fits very well. And this is the model. Okay? So everything is indoor, but the delay power spectrum, the way that they define it, they take the channel impulse response, and you remember delay power spectrum is channel impulse response squared. So channel impulse response is defined by arrival times and with magnitude of paths. Q sub tau plus phase of the paths. Okay? But if you get Q sub tau, you magnitude is squared in here, time of arrival remains the same, and phase you don't need it anymore. Okay? So this is really the physical meaning of delay power spectrum. Okay? It's a little bit simpler. Okay? Then the issue is that they come and they take this distance between these paths, very similar to in the other models. Most of the time, if you saw in the, for example, GSM, each tap was 0.1 or 0.2 microsecond apart. In here, the same. These are like TS apart. This is the TS, the sample, which is a parameter that you can change it actually if you want. Now, then the other one is that these are the number of paths. Number of paths is K max, for example, in here. Okay, which is the K max in here. Now, the difference that they have in here, they are assuming an envelope now in here. This is the envelope for the amplitudes. That's it. It's a little bit more structured. The envelope that they have considered is an exponential. This exponential envelope was the concept that originally first time came with Saleh and Valenzuela's model. They tried to just model the thing with like exponential decay. Other than that, there is no difference between what you had before. Now, mathematical computations are going to be a little bit easy in here. And so, how do you define this K max, number of paths? They have tau RMS of the area times 10 divided by TS. TS is the sampling interval. This is just one number easily you can calculate. And then, what are the amplitude of each of the paths? They are samples of this exponential, this envelope. This is the exponential. E to the minus KTS over tau RMS. Tau RMS in a sense is what? Is the value of the, the constant related to the exponential. The decay of the exponential. Decay rate of the exponential. Okay? And it's sampled at K times TS. What is the beta 0? Beta 0 is amplitude of the first one, a square. This one you calculated from what? From distance power gradient. From path loss model, for example. You can calculate it from there. Now, then, the advantage of this thing is that if I put now beta 0, if I want to normalize this, I want addition of all of these guys to be equal to 1. If addition all of these things is equal 1, Q sub tau is what? Normalized. Otherwise, I have to divide it with summation of a square of all of them. Okay. If you get the beta 0 to be equal to 1 minus this value, area under this all the time will be 1. Area under these paths. If add all of them, it would be equal to 1. Okay. Basically, what they have this exponential. Now, if you want to take it like, they define this betas of k. This is a sequence really, beta k square. This is equal to some like beta 0 square average times this exponential, which is minus k ts over tau sub m. So if I take like this thing, I can say that this is really equal to this exponential that I have in here. Beta 0, I can get it. If I get all the paths, I add them. Sigma beta k, sigma between k equal to like 0 up to, because I have the k0 in there, up to k max, okay, of beta k squares. If I get that, this beta 0k square average comes out. I have sigma e to the minus ts over tau RMS, or I call it tau m in here, or it could be tau RMS actually. Tau RMS to the power of k. Okay, this one, this thing can be written in this format. Is that right? This is an exponential k times ts over tau RMS, which is ts over RMS to the power of k. That's only an exponential. Okay? So if you take that, if you remember, like for k equal to 0 up to k max, now I have like something like beta 0 absolute value square, sigma 0 and k max. This thing I can call it whatever, a parameter, like let's say capital A, if I don't have it in here, to the power of k. Do you remember what is summation of k equal to 0 to km? A to the, that one is like beta 0 square average. It's like, I mean, summation of, I believe, z to the n or k between k equal to 0, k max, is equal to 1 minus z over 1 minus z to the power of k max plus 1. Okay, this is just something that is coming from like power series expansion. They call it truncated power series. Okay, if k max goes to infinity, it is what? It is just 1 over z, 1 minus z. Okay, that's just in. If you want to find these things, go to the definition of z transform in like Oppenheim's book. He has a lot of these summations, and you see. But this is one of that. Okay, so this would be equal to a to the 1 minus a, which is a was e to the minus ts over tau RMS, divided by what? 1 minus e to the minus ts over tau RMS to the power of k max plus 1, which is the same as beta 0 square times 1 minus e to the minus. Sorry, this is the other way around. I made a mistake. This one is the other way around. It's reverse of this thing. This is 1 minus, this is the reverse of that, over 1 minus c. Okay, and this would be then this thing to the power of k max plus 1 over this thing. Now, when k max goes to infinity, this thing goes to 1 over 1 minus c. This is where it goes. Okay. That's what will happen in there. Now, so it is equal to beta 0 times this thing. This is what I have. I made it very messy, but this is what I have in the top one, and this is the final result that I have. So summation of all these taps is equal to beta 0 squared times this thing. If I now normalize this beta 0 as the inverse of this thing, means that I put beta 0 square hat equal to 1 minus e to the minus ts over tau, I will put it just tau, over 1 minus e to the minus t over tau to the power of k plus 1. I deleted all the subscripts in there. If I put this thing, beta 0 square, equal to this value times this is equal to 1. I'm putting beta 0 square inverse of this thing. Okay? So they will equal to 1. Okay? That's exactly what they have done in here. If you come to the model in here now, so they have this exponential model. They have this exponential model for the q's of tau. Okay? Now, if you add all of these things together, which is that betas of k square average summation, if you add all of them together, okay, it ends up to that number that I find you earlier. And if you now assume that beta 0 equals to this, that number will be equal to 1. You follow? So this is only a normalization factor, really. So don't think that there is any physical meaning for that. Okay? So basically this model that they have, it has some flexibility. You give me tau RMS. How did we define the different areas in the JTC? We defined them with a tau RMS. But we defined a number of channel impulse responses. In here I have one equation with all of them. You just fitting your tau RMS in there. I think it's a nice move. Okay? And then why they are, who told them that it's decaying exponential, they go after this Saleh-Valenzuela's model. So it's a sort of fixed form of Saleh-Valenzuela model that I will show you a little bit later. Okay. Now, so it's very clean, neat. You know that how many samples you have. It depends on the TS. TS is on you. That how much, I mean, what is the tap delay line of the device that wants to implement this? That's TS. Okay. TRMS is something physical associated to the building. So I can put all of these numbers and define variety of inputs for any case with one page rather than a number of like tables. If you look at the book, for JTC I have like one appendix for all the models. In here is one page model. Okay. I think that's nice. That's good. Okay. Now, there is another thing now. If you want to simulate these things, how do you simulate these guys really? I mean, you remember that for simulation, you wanted these guys to be what? To be like, to have the certain shape. Filtered shape. Okay? Now, then, for each path, you have a complex Gaussian random variable with this variance of that path. And if you want to shape the spectrum, you have to pass it through a filter to shape that spectrum. Do you remember when you wanted to generate the paths, you had a filter, and then you run the filter with Gaussian noise, complex Gaussian noise. Okay, this is that complex Gaussian noise associated to different taps. The filter, I mean, in 802.11 they use a filter like this, which is consistent actually with the measurements that Steve had done, for example, that I showed you in like lecture 4. We saw that in indoor environment you never have. A square was the shape that they were using for what? For JTC in indoor areas. Okay, for GSM they had the double ear, which was Clark model, very good one. For indoor, however, when we saw a Steve measurement, we saw that we never had anything. But this one is very good actually, because it's easy to implement too. Ideal low-pass filter is not that easy to implement, but this one is very implement and fits with the measurements. So here we are, that we have a complete model, which is much simpler than the others in terms of presentation. But conceptually, that's the same things as others. But I like this move that now it is like one-page description rather than pages of description. Okay. Now, then you know that for the model, I have like, how many things do I have for a model, for example? I told you, I have a scattering function, which is function of like tau and f or lambda, whichever you want to call it, which is q sub tau and d sub lambda. Is that everything? Are these two functions everything that a standard activity identifies? Or we had one more piece to that. We had one more piece, you remember, path loss model. Okay? So we had path loss models that we studied the path loss models in what? In narrowband modeling. So basically, if I want to do modeling, I have a path loss model plus delay power spectrum, which is this one, plus d sub lambda, which is Doppler spectrum. Standards, they identify all of them. Now, how come GSM was not doing that? Because in GSM, you are assuming that you have Akamura-Hata's model for the path loss. Okay? For the JTC, we defined the path loss models earlier in chapter what? Chapter 4. So here we are. We can now simulate everything in terms of coverage and multipath behavior. Now, one more thing about this model is like one path loss model that is used in 802.11n SISO model. So we saw that 802.11b, they did this nice touch that they used one equation for everything. Okay? Which is also consistent with indoor modelings suggested by Saleh and Valenzuela. Now, how about the path loss models? These are the path loss models that they recommend in 802.11n, which is also applicable to 802.11b, because this is for SISO part, omnidirectional antennas. Now, what is the model? The model, they have divided the areas in A, B, C, D, E, F. From one of the people who was doing this ABCD modeling of the building, actually, one of the early ones was what Ganesh was doing, one of my students, actually. And then Steve did that. What they did is that you go to different buildings, they have different characteristics, you call them ABCD. Rather than calling specifically residential, non-residential, whatever. And for ABCD is like, you can define, but you can forget, whichever that you like. But when you are calling A like residential area, not necessarily every residential area fits to that. Do you follow me? So rather than calling residential, office, commercial, which is very good actually in terms of marketing, appearance, but in reality, really you have ABCD. And then you try to fit like A or B, C or D. You say that in this building is C model, or in that building is B model. So, but anyways, these are the path loss models that they have for that. Basically now the path loss model. Do you remember the path loss? These are, model A is a flat fading model with 0 nanosecond RMS delay spread. Okay, what does it show? It shows like short distances close to the transmitter and receiver, open areas. Because if I have only one path, I have to be in the space really. Model B. Model B is typical residential environment. You have line of sight conditions and you have 15 nanoseconds. Okay. Model C. Typical residential, a small office. It has line of sight and obstructed line of sight. This is very important, categorization between line of sight, obstructed line of sight. In reality, actually, it depends on the type of application. In the indoor environment, often we have non-line of sight because rooms are very small. In manufacturing floors, I have all line of sight. In offices, I have a mixture of line of sight and obstructed line of sight. But people see this differently. Right now, I'm doing some measurements for DARPA. What we do, we divide them like commercial buildings, manufacturing area, we call them line of sight. Residential, we call them obstructed line of sight. And then offices, we call them mixed. But in this committee, they want this type of thing. That's fine too. So these are not carved in the stone. But anyway, this is the important one. The delay spread that they associate to each of them. These are associated delay spreads. Okay? Now, you get these delay spreads, you can substitute them in what? To RMS in the previous page. In this guy. Here we are. I have the channel profile for all of them. Now, what is left? One is D sub Nanda and the other one path loss model. For D sub Nanda, they suggest a filter like this and all set. A filter like this and we are all set. So I need only the path loss. How do they define the path loss model? The path loss model that they select is like this. If you remember, I have two slopes. Do you remember? We used to call them partition models. There is one slope which comes up to distance break point, and there is another slope in here. A slope at the beginning is 2, at here is 3.5 for all of them. Look at that. But what they changed this break point. The break point for the first 4, for example, is 5 meters, then is 10, 20, and 30. That's the path loss models that they have. How about the variance of the shadow fading? These are for the first 2, then 8, then 10. So what I did in this example, actually, I combined. This is a complete example, which has what? Path loss model that we studied in chapter 4, and it has what? Delay power spectrum, which we were discussing in this chapter, chapter 6. Okay? And it's a very good example, actually. Very clean, very well structured. But remember that these models were developed like Saleh-Valenzuela's model is 86-7. And this is like 15 years after. So people get more structured, more organized. But GSM model was done even earlier than Saleh-Valenzuela's model, or around the same time. JTC model was done around 1992-3. So JTC is more structured. This one is more recent, is even more. 802.11b finalized in what? 1998. And the model came actually around 2000, after 2000, something like that. Okay? So the time passes, but people learn how to structure. But these are all engineering things. And the essence of this engineering modeling is defining three things. One is the path loss for coverage, which we called it narrowband modeling. The other one is Q sub tau, which is the delay power spectrum, which wants to tell you what are your data rate limitations. And then is what? Delay power, Doppler spectrum. Doppler spectrum is how to simulate the variations of the channel, which we have limited type of filters used in there. Either double ear filter, which is Clark's model, or uniform or ideal low-pass filter, which is the one that is used by JTC, or like a typical low-pass filter, which is used by 802.11 community. And I like that one the most because that's the simplest one for the indoor environment. Okay? So these are the models up to now. If you want to characterize, or put them in one class, the models that I told you so far, which is 802.11b and n, SISO, plus JTC, and plus GSM, all of them were assuming that arrival of the paths are fixed time. Okay? So the channel profile that I was defining for all of these models, they were something like this one, for example, which I have in fixed times. I have some arrivals like that. Okay? So arrivals are fixed. What is good about fixed arrivals? If I want to implement them with a tap delay line, I put the tap delay lines one after another. How close it is to the reality? Do you expect in reality the paths arrive in the same times? No. No. Actually, arrival of the paths, they form Poisson process at least, because they're random arrivals. Okay, could be Poisson, could be modified Poisson. Now, the first people who have to actually address this issue of arrival of the path was Professor Turin at University of California, Berkeley. He did a bunch of measurements in mid-1970s on the project, which was like collecting a bunch of channel impulse responses and see the arrival of the paths. Okay, and analyze that. And a couple of his students, like Suzuki, for example, he developed this like Suzuki distribution. That's coming. The other one was Hashimi. He did like the first channel simulator. And there are a bunch of other students that he had. They worked on this type of thing. But what they noticed was that the arrival of the path can be modeled, measured and modeled, and they are random arrivals. But later on, people, they didn't adopt that in their standardization activities because implementation of these things would have been very difficult in the old time. But now electronic is much easier. You can implement very easily the random arrivals either. But not even that. Beyond that, there was another thing. Most of the communication systems which were practical, they had limited bandwidth. they were not very wideband. So often you have 1 or 2 paths or 3, 4 paths. That's more than enough. Now you don't need to make them random. But as we are coming to the modern time, we are talking about like ultra wideband, which the bandwidth can be like 1 gigahertz, 2 gigahertz. Now I have a number of paths arriving, hundreds of paths. And now the distance between them fixed is no good anymore. So they try to model that with random arrival. Actually, the first standardization activity which started to look at things like that was ultra-wideband. Ultra-wideband, in fact, standardization activity is 802.15.3. They started to consider the arrival of the path in a random manner. Okay. Now, so that's one issue which comes to the picture. The other issue is the structure of the delay power spectrum, which is like this one, for example, that I put an envelope for that. Now, then later on, after like Turing's work, not much was done for radio channel modeling in terms of analyzing the arrival of the path, analyzing the amplitude of the paths. People were going with simple models like the GSM model, like 4-tap or 6-tap, and that was more than enough. Other people in microwave line of sight and things like that, they were using 2-path models, 3-path models, very simple models. Then in 1986 or 7, in Bell Laboratories, they started to do some measurements of the indoor radio propagation. That's around the same time that we started our program in here at WPI, actually. And then also Ted Rappaport starts his work, his PhD work at Purdue University. All of us were doing indoor channel measurements and modeling. And what happened is, one of the first group who came up with a model was this Saleh-Valenzuela, 2-person in the Bell Laboratories. And what they did actually, they went to one building, one simple building like this, which is a long, long corridor. Bell Labs, most of the places are long corridors and a bunch of offices on the side. And what they did like 125 measurements, very similar to the measurements that Turing was doing. And then what they did, they came up with a model, mathematical model, for the channel profiles. These are the channel profiles, typical channel profiles that they observed. Okay, these are typical channel profiles. So you go, our profiles were not very close to these things. But the way that they saw actually in these things, they see clusters of paths. So one cluster in here, one cluster here, one cluster, one cluster here, one cluster here, one cluster here. There is another cluster in here, another cluster here, another cluster. Means that a path does not arrive as one path. It comes in cluster of paths, and then these clusters, they get repeated. I have another. This is one cluster here, one in here, one in here. This is the way that they observe. The first people who tried to put clusters on the arrival of the path. And then they developed a model for that. And this is the model that they developed. Basically, they did, if you take, they said that we have these exponentials, exponential envelopes, which is the same thing that I told you. They are using in 802.11b. Okay? But in 802.11b, they have only one cluster. In here, they have several clusters. Okay? So I have actually now another exponential which shows connects the peak of these clusters. And then each cluster by itself has some decay. That's one difference. In here I have multiple clusters, so I need two exponential. One for the clusters themselves, one is within the cluster. Okay, that's one difference. The other difference is that arrival of the paths in the 802.11b model is what fixed, in here is random. And what they do, they assume that these arrivals are Poisson. Means that each path arrives independent from the previous path. Okay? So the equation that then it comes in here is like, I have like, these are arrival of the clusters, these are arrival of the paths within the cluster. Or they call it rays within a cluster. Okay? So I have these rays within the cluster, which are arriving at one Poisson rate, and then I have clusters themselves, which also arrive according to Poisson arrival with a different rate. So now I have 4 parameters. One is this small lambda, which is arrival rate of rays within the cluster. Big lambda, which is arrival of the clusters within the entire time. And then they have one decay, big tau, which is for big gamma, which is for arrival of the clusters. And then I have a small gamma, which is in here, which is the decay of this guy. Do you follow? So I have 2 exponential decay. One is within and one is outside. And then I have 2 arrival rate, one for the clusters and one for what? One for the rays within the clusters. With those 4 parameters, this is my delay power spectrum, which is up to here. This is very similar to 802.11b. Actually, 802.11b is similar to this because this was first. Okay, that's the reverse thing. But in 802.11b, this T sub s was fixed. And there was only, this tau KL were at fix, was KTS. And TL was only 1. Okay, in here I have expanded that. The same story. I have first path, beta 0, 0, a square average. 2 exponential are envelope of these guys. Arrival of the clusters, arrival of rays within the clusters. So this is the so-called Saleh-Valenzuela's model. If you want to compare it with Turin's model, Turin did a lot more measurements and they developed a lot of other things, and actually they showed that the arrival of the paths are not Poisson. And they also showed that the amplitude of these guys are not Rayleigh. Okay, these are result of measurements. This is a very beautiful model, excellent model, but it's based on only 125 samples, and the assumptions that they made for these paths to be Rayleigh does not fit with very wide band measurements. If you remember, I told you earlier, when you do very wide band measurements, that's the time that the magnitude is not Rayleigh, is more like what? Log normal. Because you are averaging over variations of the channel with the bandwidth. And we need this type of model for that type of application, for wideband application. So there is a contradiction. 2 problems in this model. Problem 1 is that Poisson arrival is not correct. Number 2 is that Rayleigh assumption for this is not correct for wideband communication. And we need this for wideband communication. And actually that was my first NSF grant, which resulted in the PhD thesis of Ganesh, which is one of our students. And now that PhD thesis was very useful, I believe, at least helpful for 802.15.3. Now, what we did, we said that we are going to get the Turin's work, and we want to, just like him, collect the data and actually try to measure, and based on measurement, find the statistics of arrival and statistics of amplitude. Because Saleh-Valenzuela's model assumes that these are like this and like that. Okay? But we said that we measure the amplitudes and we measure the arrivals, and very similar to Turin, we try to develop models for them. And the PhD student who worked on that was Ganesh, and he just actually showed that in indoor, very similar to the outdoor, arrival of the paths form a log normal distribution. Inter-arrival is not Rayleigh, is the so-called modified Rayleigh, which also is called delta K model. But anyway, these two models were done around 1989 and 1990, and nobody was using them until recent years when people went for ultra-wideband, and also when people started to model angle of arrival. And those are the two stories that I will follow up. Now, this is like Saleh-Valenzuela's model. What he did actually to support his model is that he takes these 4 parameters that has here and he adjusts them so that when you do the measurement, RMS delay spread of the measurement and RMS delay spread of the model, they fit to one another as close as they can be. So in here, these are result of measurement, these are result of the model. But the inherent assumption inside the model for the arrival of the path and for the amplitude of the fan, they are not validated. So it's sort of mathematical fitting. So this is about Saleh-Valenzuela's model. Now, what was important of this thing? How did this thing come up later on? Later on, people started to think about modeling for MIMO. So modeling the angle of arrival. And when you want to do the angle of arrival, again, they use the cluster model. So the beauty of Saleh-Valenzuela model, which remains there, is clustering. So if I have a bunch of arrivals, if I associate each arrival to an angle, then I can give a distribution for angle of arrival to them. And this is what that a fellow called Spencer did. Spencer did his PhD at Stanford, and in there he did the measurement, and then he went to teach in other universities, and he developed this model that he had, which that model became the foundation for 802.11n model. And that's the next part of things that I would like to talk about. Okay. Now, then I think it would be a good time right now to take like a short pause, and we start the fourth part of the lecture, which is talking about the angle of arrival.